Hello, this is David Belforti, Editor-in-Chief of Industrial Laser Solutions magazine. Welcome to the first ILS Transoceanic Webcast brought to you by Industrial Laser Solutions. Today's event, Industrial Lasers, Materials, Applications, and Innovations, will be presented by Dr. Mark Richmond from JK Lasers and Justin Conroy from Synrad. This event is sponsored by Synrad and JK Lasers. This presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. At the end of the second presentation today, I will begin asking the questions and then to the presenters, and they will be answering directly to you. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email will be sent to all registrants with a link to the archive. It will also be accessible from the ILS webpage, which is www.industrial-lasers.com. In addition to supporting audiences on the Internet using Adobe Flash and Microsoft Windows Media, Penwell now offers webcast viewing via Apple tablets and phone lines running iOS 4-2+. You will now have seamless access to both live and on-demand web presentations accessed from your iPad and iPhone. Now it gives me great pleasure to introduce Dr. Mark Richmond. Mark, it's all up to you.
Okay, good evening, everybody. It's a good evening here, and wherever you are, hope you're having a good time. I just want to spend a few minutes with you today talking about our company and just to say a little bit about what we do with our lasers and why we want to talk to you today about different materials, applications, and innovations. So I come from JK Lasers. We're part of the GSI Group, a global company. We were founded in 1972, and as JK Lasers, we have sites here in the UK and also in China, and we've been working for many years with industrial laser and different types of lasers, and more recently we've brought online our range of fiber lasers to complement the lamp pump lasers that are still around and in many applications still offer the best solution. But we want to concentrate today on the fiber lasers, and we've got a range of fiber lasers from 50 watts up to 500 watts with a single mode output power. That means there's a very good beam quality for the fine cutting that we want to do in some of the applications we're going to look at. But also more recently we have higher power fiber lasers up to a few kilowatts of power. These still offer a lot of the advantages of fiber lasers, but obviously with that higher power we're able to look at thicker materials or much faster processing. The whole range is fairly flexible, and one of the nice things that we've brought over from the lamp pump lasers into the fiber lasers is this ability to build in a timeshare or energy share unit to the laser, so that we can maximize that utilization and allow it to work in a number of different workstations almost simultaneously. So the fiber lasers, what do we mean by a fiber laser as opposed to any other sort of laser? So the fiber laser has a completely fused fiber architecture, and that means that there's no alignment that needs to be done on it once it's built, or there's nothing that's internal to the laser can get a dirty surface, so there's no more cleaning lenses or mirrors or worrying about water getting onto rod ends or something like that. We use laser diodes to provide the pump power for these devices, and that gives us very long lifetimes and very high reliability for these units. So even having a number of these diodes together, the reliability is still measured in tens of years. And the gain medium itself is part of the fiber delivery system, or part of the whole fused fiber system, and we get an inherently good beam quality from that because of the narrow diameter of it. So compared to a normal lamp pumped solid state laser, the fiber laser will give us that very good beam quality, which allows us to process into some very fine features, and we'll have a look at that a little bit later. We get the very long lifetimes and the high reliability because we're not looking to change lamps or something. We can have a low cost of ownership. The efficiency is very high. In many countries and places, having that higher efficiency really helps with reducing the heat load on the factory and also electricity costs, obviously. It also allows us to air cool up to certain powers, about 300 watts, without the need for any water cooling. And the device, compared to a solid-state laser, gives you a really short warm-up period. It really is that instantaneous power. That means you can start processing with it right away. So a number of advantages for us as manufacturers. We have to use different types of conditions, different processes for making the fibre lasers, but generally we're looking to make them in clean room type conditions, just so that as we fuse all the fibres together, we're making sure that we're not bringing any dirt or dust into it, which is going to adversely affect the laser performance later on. So I want to move on and talk a little bit about a number of applications of fibre lasers and some of the reasons why fibre lasers are particularly good for these solutions. Now, I can't obviously talk about every application in the time that we've got, so I've just picked out a few representative ones of areas that we've been involved in and seem to be generating interest for fibre lasers. And the first one I want to talk about is about medical tube cutting. Particularly, I want to talk about medical stents, which are small devices cut out from a small diameter tube, and the patterns that are used on these tubes allow them to be expanded inside the artery, and the idea is for places where the artery is getting blocked with build-up of fatty deposits, that by expanding the stent inside the artery we can open it up and let the blood flow continue in a normal way. The thing about the stents is that the kind of patterns that are cut into them are very intricate, that they need a lot of care to make these fine shapes, and the key thing here is that the quality of the cut is important, that we don't want any dross or parts which are going to later drop off or need a lot of cleaning off later on. So what we're looking at here is some of the patterns, SEM photographs of the stents, and you can see here that these are the as-cut pictures from a fibre laser cut, that the cleanliness is there. It's very, very, very clean. As we go on, and just to think about some of the things that if you're into stent cutting, if you're into this very fine area cutting, what are the things you've got to look at? To be concerned about having a small focus spot size to allow us to cut around those very fine features. We're looking for a kerf width around 20 micron, again, so that the edges and that we don't lose the shapes as we cut around very small shapes. So we're looking for a spot size, maybe half of that, about 10 micron diameter. We need to be able to provide very consistent cutting, and so we want a stable laser output power, and we need to be able to remove any of the material that we've evaporated during the cutting process, and so we use a good assist gas flow. And to do that, we need to consider both the fibre laser optically and the cutting head system. Generally, the stents are cut in a dedicated tube cutting system. It has both rotary and linear movement, and by rotating the tube and moving it backwards and forwards under the laser beam, those shapes that we saw earlier can be cut out. And also sometimes the water is flowed through the internals of the tube to provide some cooling and also to remove some dross there. What about the cutting head? So we have a cutting head which we designed to go with our fibre lasers, and it allows us to get down to about an 8 micron spot size by using different lenses inside it. But also we can see that there's an internal gas flow that gives a very good linear flow out of it, and very easy access to the cutting area. So just if you're not sure about how we work with the sort of systems that optically that are used for these lasers, then on the left hand side you might imagine that's the fibre, the light coming out from the fibre, going through the recollimating lens, There's a short period where the beam's parallel, and then it's focused down onto the workpiece. Generally, we're using a magnification here of 1:1 or usually demagnifying slightly. And by changing the ratio of the focal lenses of these lenses, we can alter the spot size and the cutting kerf width that we're using here. So when you're looking at these very high beam qualities that we get from the fiber laser single mode, then we're looking to get very small spot sizes. Any aberrations in the lens will degrade the spot performance and make it much bigger than it needs to be. So we have to carefully look at the design of the optics. But more than that, as we mentioned earlier, we have to also look at the gas flow through the head. And what we're looking at here is just the red area showing us the speed of the high-speed areas of the gas flow. So we can see the gas coming into a chamber above the cutting nozzle being mixed up and then coming out in a very parallel jet, which is very able to allow us to move out the beam. So just moving on from that, another area that's often quite interesting is welding materials like aluminium. And one of the areas where we might want to do something like this is in that little picture about a battery welding. But aluminium welding brings its own particular problems into processing because of the fact that it's very reflective at the 1 micron or so wavelength that comes out of the fiber lasers. And more than that, it just also depends on which type of aluminium has been chosen for the process and the application that is being looked at. And there's a number of different grades of aluminium, and they can give very different welding characteristics, which we have to be aware of as we're doing it. But usually the type of materials that are used are quite crack sensitive, in that if they're allowed to cool down very quickly after you've melted them for welding, they don't cool down uniformly, but cracks can form inside them. And for a typical application such as trying to weld a small lithium-ion battery package, as might be used in a mobile phone or something like that, this cracking is very detrimental to the performance of the package. And even more so in this type of application where there's a small hermetic seal is needed for this pressure testing device, and any cracks here would result in a non-hermetic seal there. So trying to make the weld as good as possible is very important. And one way to do that is to control carefully how the power is put into the weld, so that it might not just be straight on and straight off, but we want to gradually increase the power and gradually decrease it. And aluminium welding is not the only area where this sort of pulse shaping is beneficial, and there's a number of different areas on the screen here at the moment, but aluminium is probably one of the big areas. So the way to achieve that is to provide some careful control built into the laser itself. So we need a pulse generator type capability inside the laser, and then the software that's controlling the laser to have that ability to turn the laser on and off in a controlled format. And just with the software that's on the lasers I'm talking about today, and our lasers, we have a very fine control over the laser, and we're looking at some shapes here that might be used. Probably for aluminium, the bottom right-hand one there, where we bring the power on reasonably quickly, but then let it cool down quite slowly, allows us to form the weld without it cracking in the cooling down phase. So to make those shapes or any other shape, we have just a graphical editor which allows you to drag and drop and pull the shapes around to form the best one for the process that's under consideration here. Just moving on to a different type of processing, cutting now. Some materials that give us particular problems or can do are reflective materials, where we get quite a lot of light coming back from the workpiece. So we're talking about materials like copper, brass, aluminium, gold and silver. And here the reflection is high before the surface melts, but as the surface melts during the welding or cutting, that reflection can drop down quite a lot. and as the light couples in, and then the process continues quite normally. But during that initial phase, that back reflection can cause a lot of problems for the laser and for the fibre optic beam delivery system. So some applications here, we've done some. This is a tube, an aluminium tube, a thin aluminium tube. It's on a rotating stage. It was cut in about 250 milliseconds around each stage, just to trim off the end of that tube. But obviously that's aluminium, highly reflective. We've looked at copper tubes, various diameter and sizes, again highly reflective until the light couples in. We can look at different qualities of gold for jewellery type work, and again by using the right sort of beam delivery system, we can overcome the reflection that comes, or even on a coated material. There's a lot of information. I'm not going to go through all the spot sizes and the ins and outs of that, because the presentation will be available, and if you want to look back and see what the processing speeds we use, then that's very available to you. But just to give you an idea of cutting some sort of flat sheet materials, the guidelines that you might be able to expect to get with a 500 watt single mode laser into aluminium, brass and copper, around about a metre a minute or a few metres a minute cutting speed depending on the thickness. If we go up to a kilowatt laser, higher power lasers generally have a larger spot size, so we're not able to cut such fine features, but now we can cut at much higher speeds. So there's always that trade-off against power, against the speed. And often we look at this material, these sort of as graphs, looking at material thickness along the bottom, cutting speed up the side. You can see that as you go for thicker material, the intuitive thing is that the cutting speed will drop off, and it's exactly what we find. Here we see that cutting with oxygen, as we often find, is faster than cutting with an inert gas as the assist gas like nitrogen, and that's because the oxygen is an exothermic reaction and puts some extra heat into the material that it's cutting. And earlier on we talked about different grades of aluminium, and here we've got some different grades of aluminium and their cutting speeds. So the back reflection issue is a problem, and we need to overcome that, and there's lots of feedback from different people saying that they've had problems with it. So with JK Lasers we have designed a patented fibre connector into which this back reflection protection is provided, and it comes as a standard. We don't use a separate optical isolator, but the principle that we use is around the fibre we provide a very finely fitting capillary tube, and this is it just in sort of touching contact with the cladding of the fibre. So any light that's back reflected is coupled into the capillary tube, and we safely eject it sideways due to the angled end of the capillary tube. That light is collected, and we can detect that and if necessary shut the laser down, but certainly we're removing the light from the fibre before it gets to any regions where it will do any damage. If I go on to another type of welding, this is sort of agile spot welding. The example I want to look at here is hard disk drive flexure arms. A huge global market for these, and there's many multiple arms per hard disk drive, you know, for computers and other such things. So the primary consideration for flexure arm welding is there's very high cycle times, or very short cycle times, so we need to be able to move very quickly between the spot welds. The spot welds are very small because of the size of these devices, as we all know, is getting smaller and smaller, but the strength needs to be there as different thicknesses of material are joined together at different points on these weld heads, but they have to use different parameters because of the different thicknesses of material. And again, debris from spatter is not allowed at all. The clearances when they're in the read-write state is very, very small here. So typically maybe 20 spot welds, different materials, and we need to be changing maybe 6 different parameter sets through the whole of welding up just one device. So the way that we've been able to do that is that we use a scan head to move the spot around over the surface and link that up to the laser beam. There are some issues that we need to think about with using a scan head for a welding system here. If you dwell too long, or you're not dwelling long enough, if you dwell too long, the whole process takes too long. If you don't dwell long enough, you can get these sort of misshapen spots. And so we have to take great care about setting up the scanning system the control for the scanning system to allow this to work smoothly. So we can provide a scan head, a way of coupling the beam into the scan head. You can just see the blue conduit on the top of that photograph is the fibre coming in from the laser. And we've devised some software that's specially written to allow us to take advantage of the speed of the laser without running into some of the issues that come as we discussed earlier. And one of the things that's very nice about the software is in setting up this process, you've obviously got to choose exactly the right places to put the spots. So by linking up the canvas for the software to the camera, we can see exactly where those spots are going to go and appear on the workpiece at the right time. The other thing about these spots is that we wanted to get the debris down, and one way to do that is probably to change the profile of the beam. And typically the beam coming out of a fibre laser is going to be a Gaussian profile, but also by modifying the internals of the fibre laser, we can make the beam come out as a flat top profile. So the Gaussian profile beam, I mean something like this, where it's more intense on the axis of the beam and falls off to the edges. But a flat top profile would be something more like this, where there's clearly defined edges to the beam and a much more uniform distribution. If we look at what that means for the welds, we can see obviously a range of sizes for the welds, just by defocusing or changing the focus parameters as we discussed earlier. But there's a dimple in the middle of the welds, and that isn't always the profile that is wanted by customers for these type of applications. The flat top beam produces a much flatter weld and a much smoother profile, and more significantly, if we look at the cross section of those welds, we can see that the weld interface is much larger on the flat top beam than on the Gaussian beam profile welding there. So looking at the different profile of the beam can actually affect what you're doing for the actual process itself. And the disadvantage of going to these flat top beams is because we introduce more modes, we're using a bigger spot size, but in some cases that is actually just helping that process of giving you a good weld interface. So just a reminder what we mean by the flat top beam. So that is pretty much my time up, and just wanted to say that as a company, what we try to do is to make it easy for our customers by providing them a solution. We look at the laser itself, we look at the beam delivery system, we look at the process tools that are being used, and we look at the software, and we try to match all of those up to provide the best solution for a whole range of different processing examples. And so just in that quick overview, I hope just giving you a flavour of some of the things you can do with a fibre laser, and just want to thank you for spending time listening, and hand back to David, who's going to introduce the second half of our presentation.
Thank you very much, Mark. I want to apologize to you. I forgot to introduce you to our audience. Dr. Mark Richmond's product manager for JK Lasers, received his MA and PhD from University of Oxford. Over 25 years experience in the field of new technologies and laser developments. His focus now is on promoting the advantages of fiber laser technology in manufacturing processes within many market sectors. Thank you very much, Mark.
Thank you, David.
Our second speaker today is Justin Conroy. Justin Conroy is the laser applications engineer for Synrad. He's been perfecting current CO2 laser processes, including exploring cutting-edge applications in industries and fields of study that could benefit from processing materials with CO2 lasers. Justin has a BS degree in physics, and mine is in math and astronomy from Western Washington University. I now turn this over to Justin Conroy. Justin?
Thanks, David. So what I'll be talking about today is specifically CO2 laser technology, its advantages and disadvantages, the types of materials and processes it can be used in, and just some good general overall knowledge to know about our technology when you decide to use it. But before I do that, let me just talk a little bit about Synrad as a company. Synrad was founded in the 1980s in essentially a garage. First lasers were shipped in 1988, and over the years it's grown to be quite a large company. We ship thousands of lasers per month now, and we fall under the GSI group ownership along with JK Lasers. But JK Lasers deals with different laser industry markets compared to us. So part of what I'll be doing today is illustrating where we excel with our technology and what those differences are. Before I get into the specifics of CO2 lasers, let me just talk a little bit about the decision process of when you decide you want to use a laser in your industrial manufacturing system. The first thing you have to think about is the specific material you're using in your process. Depending on the wavelength of the laser you decide to use, you can get vastly different behavior in specific materials based on their absorption characteristics. A good example of this is glass. At the shorter wavelengths, like fiber and YAG, a good percentage of the beam is transmitted directly through the glass. On the other hand, the CO2 wavelength, which is much longer, absorbs very well in the glass. So for operations such as marking, you get vastly different behavior. So it's important to consider that. And then you have to think about feature size. JK was talking about doing some really small cut curve. That's because they have a small spot size due to their short wavelength. Our longer wavelength has much larger spot size, which has its advantages and disadvantages. So you have to think about how large a cut curve you need, how small your marks need to be, etc. Then you also need to think about speed requirements. Just because you have the right wavelength doesn't necessarily mean you have enough power to do it in a practical manner very quickly. And then you have to think about cost of ownership, both upfront cost and long term. Each one of these laser wavelengths has its own advantages and disadvantages in that category, and I'll be talking about that a little later. So what are some arguments for using the CO2 laser? First of all, it's a known entity. It's been used in manufacturing processes for many, many years. You know what you're going to get. It's also a low relative cost compared to some lasers, such as YAG and fiber. And its long wavelength is easier to handle from a safety standpoint. It's a little easier to beam block, etc. And then it also has superior absorption materials we characterize as organics, such as plastics and wood, and glass, which I mentioned earlier. So what do I mean by CO2 lasers? There are actually quite a few different types of CO2 lasers. So let me clarify some common types. You have high-power flowing gas lasers. Those are typically used for cutting thick steels, metals, multi-kilowatt output. They're some of the more expensive CO2 lasers out there, higher maintenance consumables. You also have TEA CO2 lasers. Those allow you to do extremely short, high peak power pulses, which allows you to do some cool things, such as doing really fast ablating and marking with minimal heat effect zone. But it's, again, a more expensive CO2 laser technology, higher maintenance. One of the cheap solutions out there is sealed glass tubes. Lower power, 20 watts to 120 watts usually, but the glass tubes don't withstand the rigors of industrial environments nearly as well as some other CO2 lasers out there, such as RF excited sealed metal tube lasers, which is primarily what we make. Those come in several different flavors. You have continuous wave lasers, which is essentially what we make. And then you also have pulse lasers, where the peak power you get is much higher than the average power. And those excel in certain areas such as drilling. So the lasers we make are just RF excited sealed CO2 lasers. We make powers from 10 to 400 watts. And we've invented several unique technologies to increase the lifetime of the lasers in industrial environments. Then a quick overview of our product line. 48 series at the top there was our original laser that we sold in the 80s. We still sell it. We still sell thousands of those per year. And for most applications, it provides very good performance. But as laser technologies have progressed, there was a demand for smaller lasers with even better performance. So we introduced the Firestar lasers, the V, the T, and the F series. So now let me talk a little bit about the technical characteristics of the CO2 laser beam. I mentioned that we have a longer wavelength laser compared to the fiber lasers that, say, JK makes. So the standard wavelength for CO2 lasers is 10.6 microns. We also make 10.2 microns and 9.3 microns for certain specialized applications. Theoretically possible to get a focus spot size slightly under 50 microns, but in a production environment, that's sometimes hard to do. So with standard optics, a more realistic spot size that you get is about 100 microns. So that means the cut kerf you can get in something such as steel is about 0.1 millimeters. Things such as plastics, the kerf is 2 to 3 times that. And then on the marking side, the minimum text height you can usually get is about 0.6 to 1 millimeter in good materials with a little melt back, and then 1 to 2 millimeters in materials which do melt, such as plastic. So how do you control the power on our RF excited lasers? All of our lasers are controlled via pulse width modulation as opposed to amplitude modulation. The duty cycles can be set from 10 to 100% power, where 100% duty cycle gives you essentially CW output. The frequencies are 1 to 5 kilohertz in operations such as cutting. On the marking side, 20 to 100 kilohertz. So you get essentially continuous looking lines. Now for performance, one of the least understood properties probably of the laser beam is the M squared value. Essentially what it boils down to is how small you can focus the beam down to, how small a spot size you can get, and as a result, how good a power density you can get. So a theoretically perfect laser has an M squared value of 1, and the higher the M squared value gets, the larger the focus spot size you get, which is not what you want, because then you have less power density. So in the example on the right, the 100-watt laser actually has better focused power density than the 150-watt laser because it has a superior M squared value. And that means the 100-watt laser was actually able to cut 15 to 25% faster than the 150-watt laser on the right. So it's very important to know what that is. Another important performance parameter is rise fall time. How quickly can the laser get up to full peak power? This is really important for engraving, kiss cutting, perfing. In the example on the right, the top line is a laser with good rise fall times. You can see that the laser was pulsing on and off really quickly. You can see each individual pulse. And then in the bottom line, it looks more continuous, has a slower rise fall time, which means the individual pulses don't have full depth of modulation, and they kind of blur together into a continuous line, which is bad, especially for things like engraving. Another parameter is peak power. I mentioned most of our lasers are CW, or continuous wave lasers. That means that at its peak power is pretty much close to what you get at full duty cycle. On the other hand, pulsed lasers can have much higher peak power than their average power, but they're duty cycle limited. And this is a benefit in certain specialized applications such as drilling. Another important parameter is power stability. In the image on the right, you see a fluctuation of only 5% duty cycle in power. The mark on the top is faded out, whereas the mark on the bottom is quite strong, and it's a very subtle change in power. So some materials are more sensitive to power fluctuations than others. So sometimes you need a very stable laser, sometimes you don't. So again, it's important to know what the material is, how sensitive it is, and just a consideration. And then some other important characteristics, which I don't really have time to go into today. Polarization, you really have to pay attention to this. When you're cutting materials such as metal, you might see differences in cut speed depending on whether you're going in the X or Y direction if you don't circular polarize it. And then there's also things such as beam symmetry, ellipticity. On the right, you see a really nice circular Gaussian mode burn in acrylic. It's from our V30 laser. So when you're doing something such as drilling, you want really nice circular holes. Important to know. So what are the types of processes you can do with our lasers? There's a lot of cutting and drilling of plastics, leather, steels, wood. We call these organic materials. We also do lots of ablating of coatings, removing layers off of shiny reflective surfaces, such as aluminum, which reflect our wavelength. We also do lots of marking, engraving, plastics, anodized aluminum, glass, etc. We do scribing in ceramic, glass, and we do a few welding apps, thin plastic films, thin steel, but it's not as large a percentage as what, say, JK does. So let me first talk about the cutting side of things. And I actually have a short video for this, so let me pull that up here. This is cutting steel. There's another option that we sometimes use as well, pure nitrogen you can use as an assist gas. Slows down the cut speed, but then you get a nice, shiny cut edge that's free of oxidation. And you can see the difference here on this slide. So on the left is a cut edge using oxygen, and on the right is a cut edge using nitrogen. Another common cutting application is plastic. Most plastics cut very well, especially thermoplastics. The best of the best is acrylic, which you see on the left there. You have a very nice, shiny, flame-polished edge. There are a few exceptions, such as PVC, polycarbonate, and ABS, which discolor. But overall, thermoplastics cut very well. On the other hand, thermosets do typically cut with some charring. So usually we only cut thin thermosets or short little degate regions, such as the circuit board on the right, if discoloring of the cut edge is a concern. Some other types of cutting. Most thermoplastic polymers cut very well at our wavelength. And one of the cool things about the CO2 laser cutting is it also seals the fabric edges together, so there's no frayed edge like you would get with traditional saw blade. And you can do it really well even at low power. Sometimes you go up to higher power though just to meet really high speed throughput requirements. Another one is leather cutting, especially in the Asian markets. Also see that in conjunction with marking. And 100 watts is generally used, sometimes more. Another common cutting application is wood cutting, especially die board is very common. Higher power, 200 to 400 watts usually needed. Ceramic and glass cutting can also be done. Unfortunately, is not as simple as other cutting of other materials. This is because when you do simple through cutting, usually you get cracking due to heat from the process. So there are advanced techniques where you preheat or post-cool to get rid of that problem, or sometimes you scribe and snap, where you scribe halfway through the thickness and then you physically snap afterwards. But the gist of it is it's not a simple process. You need quite a bit of experience in that type of process to really make it work. Okay, so now I'm going to talk about the marking side. I have a short little video to show CO2 laser marking. This is going to be marking anodized aluminum, and this is using one of our in-house marking heads. It's a high-speed galvometer system. So finishes up here. Okay, so here's some other examples of anodized aluminum marking. Very nice white contrast. Another application, which a lot of people even in the laser industry don't realize we can do, is direct metal marking on steel. Usually you need 60 to 100 watts of power to do this, though. You're not going to be able to do it with a 30-watt engraver, but we're just limited to steel. Bare aluminum, copper, and brass completely reflect our long wavelengths, essentially. So we're limited to just steel. And the mark is very superficial. There's not much depth, unlike deeper marks you might get with shorter wavelength lasers. Plastic marking is also very common. Thermoplastics, again, just like cutting, they don't discolor when you try to mark them. So the marks we get don't have an actual color change. You do often get readable contrast. You can do it at low power, but it's not going to be a high contrasty mark. Now, on the flip side, the few exceptions we talked about, such as PVC, polycarbonate, those do turn a nice color when you try to mark them, which is bad for cutting, but great for marking. Another common one is circuit board marking, 2D codes especially. We're able to blade off the solder masks without damaging the copper underneath. The copper reflects our long wavelength, so there's no damage to the traces underneath. You can do it at 10 watts of laser power very quickly. Another common one is glass marking. We often replace sandblasting, get nice white marks. And quickly, just a few other common marking applications we see. Button marking. Buttons are usually made of plastic or wood. Get some nice high contrasty marks. They're often coated too, so we blade off the coating. Do that low power. We also blade off inks off of cardboard or paper packaging very easily. So you can see the barcode on the right over the purple ink. We've bleached out the purple ink, leaving the barcode. Again, low power. Another common one is ceramic marking, chip and fuse marking. We can do it 10 to 30 watts, get a bronze or silver contrast, usually very high contrast. So that's all I'm going to talk about for marking. There are a couple other processes I want to talk on briefly that are very common as well. One we're seeing an increase of interest in is wire stripping. The CO2 laser wavelength is uniquely suited for this type of thing because the plastic jackets absorb our wavelength very well, but the copper wire underneath reflects our long wavelength, so we're able to easily remove the jacket without damaging the wire. Another one is high-speed drilling and trepanning. We're replacing a lot of traditional drill bits and saw blades in applications such as this. As you can see, the drill bit hole on the right, not very clean looking, pretty ragged, whereas the laser cut hole on the left, very clean looking. And then welding. We can weld some plastic films very well, especially polyethylene. Polyethylene tends to be the best of the best. And then we do some thin steel welding as well. Generally, we need to go up to our higher power lasers to do this, around 400 watts, and usually just thin steels. So I mentioned we make a couple of alternate wavelength lasers as well. We make 9.3 and 10.2 micron in addition to 10.6 micron. 9.3 micron wavelength is best suited for materials such as PET and Kapton. A good example of the 9.3 advantages is soft drink bottle marking, which are PET bottles. The 9.3 mark is a nice crisp white contrast, whereas the standard 10.6 wavelength is more of a transparent mark, not nearly as visible. So next time you go to the grocery store, you look at the date code, very possible that it's a 9.3 wavelength mark. 10.2 is well suited for a lot of thermoplastic films, high-speed cutting and perfing, especially those that have polypropylene content. The food industry especially seems to have an interest in this. Often you have these multi-layer food packaging where you want to perf a tear line, but you don't want to go all the way through the package. So the top layer will be polypropylene, which absorbs the 10.2 wavelength really well, and then the bottom layer will be a different type of plastic. So with the 10.2 wavelength, you're able to selectively perf that top layer without damaging the bottom layer. And then, as I mentioned before, most of the lasers we make are continuous wave. We do make some pulsed lasers, which we are about to introduce. The first of those being the P100. So you have much higher peak power compared to average power. And this benefits you in material processing, which requires high peak power, such as steel cutting and high-speed processes where you need to perf really quick. And it minimizes your heat effect zone because you can do things quicker. So for specialized applications, pulse lasers provide a significant leg up. And I'm about to wrap it up here, but I just want to make you aware that we have a lot of resources available on our website. You can search videos, applications, play around with some interactive web applets. We also have a monthly newsletter where you can learn about the latest and greatest. And we have a fully functional applications lab where we can test your project. And with that, I'd like to thank everyone for attending, and I'll throw it back to David here.
Thank you very much, Justin. Ladies and gentlemen, we are now going to answer some of the questions that have been coming in. I'll address them to the presenter, who can perhaps ask them more appropriately. The first question goes to Mark. How much power per watt will it take to cut a millimeter thick sheet of gold or silver?
Well, the example I gave, we were cutting just about a 0.7 millimeter thick gold sheet at about with 200 watts. I think as you go to the higher, thicker materials, we'll need about 400 to 500 watts of average power to cut through that cleanly. Obviously, it depends a little bit on the required cutting speed and the quality of the cut that's needed, but around that 400 to 500 watts should be very doable.
Question for you, Justin. What's the best wavelength of CO2 for cutting acrylic, extruded acrylic, or cast acrylic?
Generally, we use the standard 10.6 micron wavelength for cutting acrylic. There are some subtle differences when you're cutting extruded and cast acrylic. Generally, we find that cast acrylic flame polishes a bit better than extruded acrylic. But yes, 10.6 microns generally is what you'd use.
In that same vein, Justin, what materials or applications are best suited for 10.2 and 9.3 micron CO2 laser sources?
Well, I think I covered a couple of those at the end. For 10.2, it seems like the plastic converting industry and packaging is where the most interest is, because they need to do high-speed operations where, you might have great perf quality at 10.6. Like a lot of these plastic films perf great at 10.6, but if you get, like a 15 or 20% increase in speed by going to 10.2, and you're minimizing slight heat effect quality, then it makes sense to go to 10.2. It's a refinement of the process. And with 9.3, I think, like I said before, the beverage industry with the PET bottles, you look in the supermarket, most beverage bottles out there are some form of PET, and most of the date codes now are laser marked. You still see some ink dot prints, but often you can't read them. So there is still kind of this transition towards laser marking. And that would be with the 9.3 wavelength.
You're still up, Justin. What determines the M-square value other than a tighter focus?
What determines the M-squared value? So the M-squared value is just a ratio of the initial beam waste and its divergence. So you need a laser with, so say you have a laser that has a fairly large beam waste, then you want that to have a low divergence. If it has a high divergence, that means your M-squared value will be larger, and you won't be able to focus it down to as small a spot.
Can I just chip in there a little bit, as Mark here, just because we've been talking about both CO2 and fiber lasers today. With the difference between the 1 micron and the 10 micron, there's also a wavelength dependence on that M-squared. So an M-squared of 1 at 1 micron, which is like a fiber laser, is a different sort of focusability than an M-squared of 1 for a CO2 laser at 10 micron. So in fact, you'd expect those beams, the 1 micron beam, to be able to be focused 10 times smaller than the M-squared of 1 at 10 micron. So you just got to be a little bit careful just when we compare between one laser and another, that we're comparing like for like, and it's not always easy with a CO2 and a fiber laser just to compare that.
Don't go away, Mark. Here's a question for you. The fact that multi-kilowatt fiber lasers are already widely used in industry means that other manufacturers have also overcome the back reflection issues that you mentioned, does it not?
Well, yes, there's different ways that that can be done. For instance, some of them process with the focus head at a slight angle, but that can introduce a bit of astigmatism into the cut and not allow you to cut the best conditions. A lot of the multi-kilowatt fiber lasers are used for cutting mild steel or stainless steel, fairly thin sheets at high speeds where the coupling in happens very quickly. And in that case, we're into the melt regime, and then you're not getting very high levels of back reflection. And that occurs well if everything's set up correctly. If, for instance, something goes wrong and you're a little bit out of focus or your sheet moves, then you can start to, even in those easy materials like mild steel, stainless steel, start to get high levels of back reflection. So, the feedback that we're getting from the market is that back reflection still is an area of concern for fiber laser users, and that having a built-in system gives a good peace of mind just to add to the capabilities of the fiber laser. So I'd just answer like that.
Question for both of you. How does cost per watt compare between fiber laser and sealed metal tube CO2 lasers? Mark, you want to go first?
Well, I would say that there's a crossover, and I think when you're looking at the low power lasers, maybe less than a few hundred watts, then the CO2 is probably going to come out as the lower cost option. As you move up to the top end of the range, the CO2 lasers tend to get quite large, but the fiber lasers above maybe 400 or 500 watts, where you're topping out on the sealed tube systems anyway, they come in much better, lower cost. When you get to the really high powers, sort of kilowatt type fiber CO2 lasers, which are used for a lot of the flatbed cutting applications, then again the CO2 lasers at those multi-kilowatt levels are probably around about the same sort of price now as the fiber lasers, possibly still a little bit cheaper for a CO2 laser. I don't know what Justin thinks about
yeah, I would agree with what Mark said. And it's kind of a difficult question, too, because, there's some overlap with the applications we do, but, there might not be a good solution for certain materials at a certain wavelength. Like I said, we can't cut, say, copper or brass at all. That's something you'd have to go to a high-power fiber laser anyway to do. But then if you're just perfing, say, a plastic bag, or you're doing a date code on a bottle, you can do that at 10 to 30 watts. And it's going to be a lot cheaper and get better performance than you ever would from a fiber laser. So it's really picking the right tool for the job. They're really two different tools. So trying to equate them as being the same thing is, you have to be careful with that.
Justin, regarding wire stripping on copper due to the wavelength, is there a concern of using maximum power, say 10 watts on a thin copper sheet, of damaging the copper?
No. We've never had issues damaging the copper. Even you go up to like 100 watts even. We have people wire stripping using 100-watt lasers, and there's still no apparent effect on the copper. You can't tell that the beam's hitting it at all. Now, in certain cases, if you go up to higher power, you might have to worry about back reflection a little bit, so your angle of incidence isn't straight down, but overall damage to copper from our wavelength is just not a concern. It's just not an issue.
Mark, when working with a fiber laser through a 50 micrometer fiber, what is the maximum spot size that one can usually get?
Well, typically with a focus head, without it getting too cumbersome, you're going to look at about a 3 times expansion magnification on that. So you're probably going to look with a 50 micron fiber being able to go up to maybe 150, maybe 200 micron spot size. With a lot of the higher power fiber lasers, though, it's possible to use a different fiber. There's a detachable fiber. You can plug in a different size fiber if you need to go to those bigger spot sizes, and then you can maybe plug in a 200 or 300 micron core size fiber, and you'll be able to get to the bigger spot sizes if you need them. But with a 50 micron fiber, you should be okay up to 150 micron or so.
Back to you, Justin. What is the range of scanning speed for marking applications? And a follow-up question to that, can you cut thin aluminum foils, say 6 to 50 microns thick at high speeds?
Well, first the scan speeds. That's kind of up to your beam delivery. We have a couple of marking heads in-house which can go maximum speeds 200 to 300 inches per second, so very fast. The video you saw of the marking, the race car, that was a scan speed, I believe, of about 75 inches per second. The mirrors scanning the anodized aluminum. But it really depends on, I mean, it's really as quickly as you can scan it, you know. And our specialty isn't scanning mirrors. It's primarily just CO2 lasers. On the thin aluminum foil, I kind of brushed over this. We can cut thin aluminum foil starting at about 200 watts, but this is with a cutting head where you'd be using a sysgas. But the cut is not very quick, and the edge can sometimes be pretty ragged too. So we can cut thin aluminum foils, but not with a scan head, just a standard cutting head using a sysgas. 200 to 400 watts, and the cut edge isn't that great. And you have back reflection problems too, so you typically need to put in an optical isolator. So
this might be one of the cases where Justin was talking about earlier, we're using the right laser for the job, because and that cutting an aluminium foil with a scan head is something that you can do with a fiber laser. So it's, you know, obviously if you've got a CO2 laser and you want to go that route, then it can be done. But if you're just starting from scratch and thinking what's the best route, you may want to consider the fiber laser route in there as well.
Yeah, aluminum foil cutting is not one of our advertising bullet points. It's one of those things where if you have a cutting table, you're cutting a bunch of plastics, and then occasionally you might want to cut some aluminum foil. That might be something good to know. But if your system is primarily going to be cutting aluminum foil, I would say go with shorter wavelength laser.
In regard to cutting materials that are difficult to cut, Justin, what about your comments on thin thermoset materials? Do you typically use a gas assist?
Yeah, we use generally air. Sometimes we'll use pure nitrogen. Sometimes getting rid of that oxygen can help reduce the discoloration some. We're also seeing, like with the new P100, the pulse laser, if you're able to quickly deliver the energy in high energy pulses, sometimes you can reduce the discoloration as well. You can't eliminate it, but it helps.
Again, another question on edge conditions. When you're dealing with biological materials with a CO2 laser, how do you minimize the burning effect?
How do you minimize the burning effect?
On biological materials.
Biological. So are we talking, I guess I'm not sure. Are we talking about, like, I guess I'm not sure what biological, are we talking like just organics, like plastics? Are we talking about, I guess I'm not sure what that question's asking.
Well, maybe they can contact you directly. You can contact them afterwards.
Yeah, that's kind of an open-ended question. I probably need more details to be able to adequately answer that.
In regard to the pulse laser, Justin, can you elaborate on the effect altering the kilohertz input to the laser would have on cutting or marking textiles?
Cutting or marking textiles. What the pulse width would do? Well, it would depend on what you're trying to do. If you're trying to do high-speed cutting, you might shorten the pulse width a bit, increase the frequency. Usually on textiles, though, CW works really well. So I'm not sure that the pulse, a lot of times we just run the laser more in CW mode where we set the duty cycle really high. So it's not even really pulsing at that point. It's more just continuous wave, because you want kind of this continuous sealing process in the textile. You don't want any frayed edges. So it's more of a CW application.
Okay, Mark, how about the fiber laser being used to cut indium phosphide or gallium arsenide wafers for semiconductor processing?
Well, we certainly used the fiber laser for cutting silicon wafers, and had some very good results in cutting the thin foils up to about 1 millimeter thick on the silicon. Not sure that we've actually particularly looked at the other gallium arsenide indium phosphide situations directly. So our best experience is that yes, we can cut silicon and get good edge quality and no cracking, but up to about 1 millimeter with a few hundred watts. But we haven't directly tried the gallium arsenide wafers. But it's something that could be looked at, and there's a good chance it would work.
Okay.
But, without trying it, we can't say directly.
Tell me, how fast can you directly modulate fiber lasers? Are there any external modulation optims for greater than 100-watt beams?
Yes. So the direct modulation that we put onto the fiber lasers, we run them up to around about 50 kilohertz just by directly modulating the power source into the laser. And that really sort of takes into account the rise and fall time. If you try to go much faster than that, the output pulse doesn't really follow the demand signal that you're putting in. If you want to go faster, yes, people do use fiber lasers with external acousto-optic modulator devices to provide very fast switching of the pulse on and off for applications in some of the printing industry applications. And then the question really becomes then is what speed do you want to go at, because the power handling capability of the acousto-optic modulator tends to increase with the aperture, but also the speed drops down as you go for larger aperture devices. So it's a bit of a trade-off there in terms of the power handling and the switching speed of the device.
Mark, with the interface that was shown for the fiber laser, was that a real-time camera image of the part? Was that through a galvo? Yes. With that
software, we can in real time look at an area around where the beam would land. We can in real time move the mirrors effectively, and therefore change the area or the position that we're looking at on the galvanometer, so that while we're setting up the job, looking where the pulses are going to appear onto the workpiece, in real time we can see that picture changing, so that we know that we're putting the laser beam down exactly onto the workpiece in the place we want. So yes, it's a real-time picture, and actually having that facility does in fact dramatically reduce the setup time for a new job, whereas you can just download the pulses from a DXF file or something, get them roughly in the right place, and then fine-tune it in real time by watching the pulse and just seeing how your parts really behave underneath the laser beam.
Thank you very much. Well, Mark and Justin, we still have a few questions that we could answer if we haven't run out of time. We've actually gone over our allocated time. I would advise everybody that your questions are logged in, and the presenters will get back to you by email to answer the specific questions you might have, especially those that were very detailed about certain materials and other comments on procedures for specific materials. On behalf of Industrial Laser Solutions and Pemwell Corporation, I would like to thank today's speakers, Dr. Mark Richmond from JK Lasers, Justin Conroy from Synrad, and our sponsors, Synrad and JK Lasers, for today's presentation, Industrial Lasers, Materials, Applications, and Innovations. This presentation will be archived within 24 hours and can be accessed from the home page at www.industrial-lasers.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to meeting you again in future webcasts. Thank you again, gentlemen. Good day.
Thank you. Goodbye.